So this is the block diagram of the second SSB receiver, which is called SSB envelope detection receiver. Through the receiver antenna, we will receive the SSB signal. It could be single sideband suppressed carrier, in which case carrier needs to be generated locally in the demodulation process, or it can also be single sideband reduced carrier form. Now please note that in the second approach, where we add the carrier signal to the SSB signal and pass it through the envelope detector, it becomes very essential that the carrier signal that we use comes from the received signal only, because in that case the carrier signal used on the receiver side and the carrier signal used on the transmitter side will be exactly same. And hence in the second receiver we always use the transmitter system which is transmitting single sideband reduced carrier version of the signal. So we will extract the carrier signal from the incoming signal only and not generated locally. But please remember that we are going to use the super heterodyne receiver, super heterodyne concept, because we want to avoid the receiver operation at high frequencies. So let's say the incoming signal is present at some station frequency Fs, which is also the carrier frequency. The first block as usual is RF amplifier with pre-selector. Pre-selector will select the desired signal coming from the radio station to which the receiver is tuned. RF amplifier will amplify the incoming signal. The output is given to the RF mixer. The RF mixer is nothing but the mixer which is used for the down conversion. First frequency will be the SSB-RC present around Fs. The second frequency is the frequency of the local oscillator. The frequency of the local oscillator, which is F4, is equal to Fs plus IF. Now instead of using single local oscillator, we are using a circuit which is called carrier recovery and frequency synthesizer. We will discuss this circuit, this block in a brief. Carrier recovery block is nothing but the block which will recover the carrier from the incoming signal. You can see that the incoming signal is given to the carrier recovery block as it is. So whatever is my incoming signal, let's say if it is in the form of cos 2 pi fc plus fmt, which is the upper sideband, but along with this upper sideband, very highly attenuated, so I'm using amplitude AC dash cos 2 pi fct, very highly attenuated. This AC will be very much less than 1. Highly attenuated carrier is also present because it is single sideband reduced carrier. So the function of this block will be to extract this carrier signal. And once that is done, what we have got is we have got a single frequency sinusoidal signal 2 pi fct. Now what will frequency synthesizer do? Frequency synthesizer is a block which is capable of generating variety of frequencies. For example, it can generate the harmonics of Fc. It can generate the cross products of Fc, that means Fc plus Fm, F1, Fc minus F1, where F1 will be some internally generated frequency. We right now want frequency F4, which is Fs plus If. Let me remind you that Fs plus If will be exactly same as Fc plus If, because Fs is the notation we are using for Fc. To generate Fc plus If, Fc is already there from the carrier recovery circuit. If will be generated internally and frequency synthesizer will generate the sum of the two frequencies. So output of the frequency synthesizer block will be one frequency Fs plus If. Somewhere in the later part of the receiver, I'll also require only this frequency If. So the carrier recovery and frequency synthesizer block will also generate another frequency which is If independently. So I repeat, it gets carrier frequency from carrier recovery block. There will be an oscillator inside which will give us the intermediate frequency generated, or even if there is no oscillator, from the recovered carrier signal only by performing various operations we will generate the intermediate frequency. Once we have Fc and If, we can generate the sum of the frequencies Fc plus If, which is used with the RF mixer, and we can also use If as an independent frequency later on. So ultimately we come to a conclusion that mixer takes two inputs, one present around Fs and one Fs plus If. So output of mixer will be the signal present around If. To be precise, it will be the signal from If to If plus Fm, which represents upper sideband. This represents upper sideband present around intermediate frequency. Extracted using a bandpass filter, it is given to IF amplifier so that the entire signal is amplified. Now comes into picture the demodulator circuit that we have discussed. The output of IF amplifier will be nothing but the exactly same signal which was present at the output of the mixer. It is just amplified, that's it. So output of the amplifier is now given to the linear summer. What do you think will be the second input to the summer? Let me take you to the previous slide where you can see we were adding incoming signal with cos 2 pi FCT because incoming signal was at carrier frequency FC, which is not the case anymore. The incoming signal is now converted to the IF intermediate frequency, so we are going to add the frequency which is cos 2 pi into IF into T. Once you add the two signals, the output will be nothing but single sideband full carrier which will have a well-defined envelope present. And once we have this envelope present, I can give this signal to the envelope detector, and hence output of the envelope detector will be demodulation information in the form of M of T. So that explains the entire receiver which operates on the second approach of demodulation, where you convert suppressed carrier or reduced carrier signal into full carrier signal and pass it through the envelope detector. We have discussed a new block in this receiver which is frequency synthesizer, which uses one frequency or two frequencies and generates various combinations of the frequencies.